On January 16, 1943, the SS Schenectady rested quietly at the docks in Portland, Oregon. A brand new Liberty ship, only 10 weeks old, fresh from the Kaiser shipyards. There was no storm that day, no enemy threat on the horizon. The morning was calm, the waters still. Then, without warning, a sharp crack shattered the silence. In seconds, the entire vessel fractured in two, the hull splitting from deck to keel as if cleaved by an invisible hand. Sailors scrambled for safety as the bow and stern sagged in opposite directions, the ship's back broken while still tied to the pier. The Schenectady wasn't alone. That same winter, the SS John P. Gaines broke apart in calm seas, and the T-2 tanker SS Schenectady's sister ship, the SS Manhattan, cracked so violently her crew fled in panic. Between 1943 and 1944, over 2,500 Liberty ships reported major structural failures, hull cracks, deck fractures, catastrophic splits. 19 ships broke completely in half, and at least 3 vanished without trace, disintegrating so quickly they never sent distress calls. These weren't the results of torpedoes or storms, they were ships destroying themselves. The United States had gambled everything on the Liberty ship program. After Pearl Harbor thrust America into total war, the nation needed cargo vessels by the hundreds and fast. Traditional shipbuilding took 8 months per ship, but that timetable was impossible. Then came Henry Kaiser, an industrialist with no shipbuilding experience, who made an extraordinary promise: mass-produce freighters like automobiles, rolling off assembly lines in weeks instead of months. At his Richmond, California shipyards, he introduced revolutionary methods: welding instead of riveting, prefabricated sections instead of hand-built construction, and assembly line logistics borrowed straight from Detroit's car factories. By late 1942, Kaiser's yards were launching Liberty ships in an average of just 42 days. It was hailed as an industrial miracle. Propaganda reels showed women welders, Rosie the Riveters, though they wielded torches now, transforming steel plates into ocean-ready freighters at impossible speed. The SS Robert E. Perry set a record that November, built in only 4 days and 15 hours from keel to launch. Across the country, Americans cheered as new ships surged into the Atlantic, reinforcing Allied fleets decimated by German U-boats. Then the triumph turned dark. Ships began breaking apart, not from torpedoes or rough seas, but spontaneously, catastrophically, in perfect weather. Naval engineers were stunned. The welds were solid, the steel met all specifications, the blueprints had come from proven British designs, yet Liberty ships were fracturing like porcelain teacups. Cracks formed at hatch corners, gun mounts and squared hull edges, racing through welded plates at terrifying speed, sometimes splitting an entire ship in seconds. The Maritime Commission launched frantic investigations. Metallurgists studied broken hulls under microscopes. Engineers rechecked stress data. Inspectors crawled through ruptured ships searching for answers: bad steel, poor welding, flawed design, or sloppy quality control. Still, ships kept breaking while committees argued. Sailors began fearing their own decks, knowing at any moment the hull beneath them might unzip into the freezing Atlantic. The miracle of mass production had become a nightmare, and no one could explain why. The answer came from an unlikely source: a welder named Bessie Hamill, working the night shift at Kaiser's Richmond Yard No. 3. Like thousands of women who had replaced men sent to war, she'd been welding for 8 months and had begun noticing something the engineers missed. Each night, she saw teams welding the massive steel plates in sequences that defied mechanical logic, starting at edges instead of centers, or running single seams from end to end without pause. As each weld cooled, the metal contracted, twisting and pulling the plates into tension she could see and feel. By the time one section was complete, the structure was already locked with invisible stress. It was like tightening the center bolts of a wheel before the outer ones, an invitation to failure. Her concerns were dismissed. She was just a welder. But Hamill persisted. In November 1943, breaking protocol, she requested a meeting with supervisors and brought test plates she'd welded on her own time. Those welded edge to center showed clear warping. Those welded from center outward remained flat and true. Skeptical but curious, one supervisor came to observe her shift. What he saw was undeniable. The welding sequence itself was torturing the steel, creating residual tension that never left the structure. Each weld cooled unevenly, locking stress into corners and seams that would later snap in cold seas. Hamill's solution was simple yet brilliant: weld from the center outwards, letting stresses dissipate naturally, Alternate welding locations to avoid overheating. Never weld entire seams in one pass. These weren't theories, they were practical truths from someone who felt the metal respond under her hands. By December 1943, her observations reached Henry Kaiser himself. He faced a painful choice: admit that every Liberty ship carried built-in flaws, halt production to retrain thousands, and redesign his entire process, or risk more ships splitting in two. To his credit, Kaiser chose the truth. Tests were ordered immediately. Engineers and metallurgists, once skeptical, followed instructions from a woman who'd never set foot in an engineering classroom. The results were startling. Hull sections built the old way showed residual stresses exceeding 30,000 pounds per square inch at critical points, while Hamill's sections peaked at only 12,000. The steel and weld chemistry were identical. The only difference was the order of operations. The implications were undeniable. The mystery was solved. Steel is not static. It's crystalline, alive to temperature and tension. Welding heated it beyond 2,500 Fef, expanding it violently. Cooling locked that expansion into the hull unless the weld sequence released it. The Liberty ship's failures were a perfect storm of physics: poor welding sequence, cold Atlantic temperatures, and brittle steel. The shipbuilding steel, strong in warm water, became fragile below 40 degrees Fahrenheit. Instead of flexing under strain, it shattered like glass. When combined with residual stress and sharp hull corners, microscopic cracks became lightning-fast fractures, racing across plates faster than sound could travel through metal. The SS Schenectady's sudden break now made perfect sense. Built in early winter, welded in stress-maximizing sequences, her hull carried millions of pounds of locked-in tension. When the cold Portland air hit that brittle steel, the ship didn't just fail, it tore itself apart. When morning temperatures dropped to 28 degrees, the steel turned brittle. At one hatch corner, the stress concentration ignited a crack that raced unchecked through continuously welded deck plates. There were no riveted seams to slow it, no stress relief brakes to stop it, and in seconds the fracture consumed the ship, releasing decades of stored energy in one catastrophic failure. Traditional riveted ships never suffered this problem, and the reason explained why welding seemed cursed. Riveted construction was inherently discontinuous, each plate a separate element, each joint a natural barrier. Cracks that began in one plate hit a riveted seam and stopped. Overlapping plates and mechanical fasteners acted as built-in crack arresters. Welded ships, by contrast, were continuous structures. A single fracture could travel unhindered for hundreds of feet through welded seams. The very efficiency that made them faster to build also made them dangerously vulnerable, in ways riveted ships had never been. The Liberty ship's squared-off design worsened the flaw. British maritime architects had chosen hard corners to make cargo loading easier, never realizing that sharp internal corners multiply stress by enormous factors. Every ocean wave flexed the hull, sending stress spikes through those corners. Combined with residual welding tension and brittle steel, they became perfect crack initiation points, waiting for the right conditions to fail catastrophically. Henry Kaiser knew exactly what these test results meant for his empire and the war effort. In January 1944, he made a decision that could either vindicate his industrial revolution or expose him as a reckless profiteer who had sent thousands of sailors to sea in defective ships. He halted Liberty ship production at Richmond Yard 2 and diverted resources to an entirely new vessel, the Victory ship. It wasn't a minor change, but a fundamental redesign built around Bessie Hamill's welding discoveries and the harsh lessons etched in fractured hulls across two oceans. The gamble was immense. The Allies still desperately needed Liberty ships. U-boats had already sent more than 2,000 merchant vessels to the bottom since 1939, and the upcoming invasion of Europe demanded the largest amphibious logistics operation in human history. Every ship mattered. Yet Kaiser bet that he could implement Hamill's sequenced welding system, redesign the hull to eliminate stress concentrations, improve the steel specifications, and still maintain the unbelievable production speeds that had made his yards famous. Competitors called him insane. Congressional investigators waited, ready to crucify him if production collapsed. But Kaiser's engineers worked backward from every failure. Every square corner in the Liberty design was replaced with rounded transitions. Hatch openings, once breeding grounds for cracks, were redesigned with generous radii to diffuse stress. Plate thicknesses were recalculated, not merely to add strength but to balance stress distribution with the new welding sequences. Structural frames were repositioned to align with natural stress relief points rather than resisting them. Even the steel itself changed. Kaiser's metallurgists specified a new alloy with improved low-temperature toughness, slightly reducing carbon content and increasing manganese. Small additions of nickel, expensive and rationed for armor, were justified when tests proved that even 0.25% dramatically improved resistance to brittle fracture. The Maritime Commission balked at the cost until Kaiser demonstrated that preventing just one ship loss would pay for the upgraded steel in 50 vessels. In March 1944, the new specification was approved. Then came the hardest part, retraining an entire workforce. By early 1944, Richmond shipyards employed over 90,000 people, thousands of them welders trained in crash courses to lay straight beads quickly. Now they needed to master sequencing, stress relief, and thermal management. Kaiser established welding schools within the yards, pulling skilled welders like Hamill from production lines to teach. Every worker received a numbered sequence card for each hull section. Weld 1 here, weld 2 there, never out of order. Prefabrication expanded dramatically. Instead of welding large sections in place where stress was hard to control, planners broke victory ships into smaller modules built in specialized shops. A bow section might include 50 sub-assemblies, each welded under controlled conditions using the prescribed sequences, then stress relieved in heating ovens before final assembly. This modular approach let welders work outward from each section's center, exactly as Hamill had shown, without the constraints of a full hull. When the first victory keel was laid in February 1944, construction took 18 days, slower than Liberty records. Critics pounced, declaring the program a failure, proof that quality and speed couldn't coexist. Kaiser ignored them. He watched the crack inspection reports instead of the calendars. The first 2 victory ships showed 0 stress cracks, not fewer, none. By April, Richmond Yard 2 had become a choreographed marvel of steel, fire and coordination that would have seemed impossible 2 years earlier. The yard no longer resembled a shipyard, but a vast assembly plant, an industrial ballet of prefabrication zones feeding a central line where hulls took shape with breathtaking rhythm. Kaiser had borrowed Henry Ford's assembly line concept, but here, instead of moving the product, specialized teams rotated between stationary stations in timed intervals. It began in giant prefabrication sheds, where welders built hull sections under 30 feet in size, each governed by a sequence card, 47 color-coded welds per section, always starting at the geometric center and spiraling outward. Supervisors checked every step. After 10 welds, each section was heated to 2100 degrees, then slowly cooled to relieve stress. Steel plates arrived pre-cut, pre-formed, and precision-drilled from retooled rolling mills. Curved bow sections came ready-made, deck plates pre-drilled, frames pre-assembled. Controlled factory prep eliminated variables, ensuring identical quality across thousands of parts. On the building ways, assembly followed a radically different rhythm, not from keel up, but through simultaneous module construction. Engine rooms, cargo holds, bows and sterns were built in parallel, then lifted by massive gantry cranes in one coordinated ballet. On May 12, 1944, 17 major modules, 85% of a full hull, were positioned and aligned in just 11 hours. Welders joined the sections using the same center-outward pattern, but now they were linking stress-relieved modules instead of creating new stressed ones. The legendary 5-day timeline emerged from relentless refinement. Night shifts staged materials for day shifts. Specialized teams inspected alignment and weld quality in real time. Mobile cranes moved on fixed 5-minute routes. Welders rotated 30 minutes on, 10 off, sustaining precision without fatigue. Kaiser implemented his critical path system, tracking bottlenecks and shifting crews dynamically to keep every phase balanced. Every delay was documented, every fix analyzed the next morning before it could repeat. Then came June 27, 1944. The SS Benjamin Warner, victory ship hull number 23, was completed, from keel laying to sea trials in just 5 days and 11 hours. Not a strict demonstration, but a fully equipped combat-ready cargo vessel with armaments, power systems and engines intact. Her post-construction inspection revealed no cracks and normal stress levels. When the Warner sailed on her shakedown cruise, she performed flawlessly in conditions that had destroyed early Liberty ships. The 5-day victory ship wasn't just proof of speed. It was proof that engineering discipline, when aligned with human will, could rewrite the limits of industrial creation. Bessie Hamill's observation had reshaped the very foundations of industrial shipbuilding. The victory ships born from Kaiser's redesigned system were entirely new vessels, revolutionary at every scale compared to their Liberty predecessors. To the casual eye they looked similar, Ordinary cargo haulers with the same purpose, but their differences began at the molecular level and extended through every aspect of design and construction. Where Liberty ships had been emergency stopgaps, Victory ships were engineered solutions, refinements written in the blood of sailors who had gone down with fracturing hulls in the cold Atlantic. The new steel specification proved vital. This alloy, known as killed steel because aluminum was added during production to remove oxygen, showed dramatically improved toughness at low temperatures. Tests revealed the transition temperature, the point at which steel turns brittle, had fallen from roughly 40 SAF in Liberty steel to just 5 FF. That 35-degree improvement meant Victory ships retained flexibility, where Liberty hulls became fragile shells. The cost increase was 8% per ton, but the benefit was beyond calculation. Every structural detail embodied new understanding of stress concentration and crack propagation. The rounded hatch corners, once thought aesthetic, reduced local stress by more than 60%. Sharp 90-degree corners in Liberty ships had multiplied stress by nearly 4. Victory ships' generous radii brought that multiplier below 2. In practice, a wave impact that might have torn open a Liberty ship only flexed a Victory hull within safe elastic limits. The hull plates themselves incorporated crack arrestor features, riveted seams strategically placed at intervals to break up continuous welds. These hybrid connections created intentional discontinuities, places where a propagating crack would meet resistance and lose energy before it could consume the ship. The design accepted that cracks could start but ensured they would not spread unchecked. It was defensive engineering, anticipating failure instead of denying it. Structural frames were doubled at critical points, creating redundant load paths so if one frame cracked, its neighbor carried the strain until repairs could be made. Liberty ships had no such mercy. One failure often cascaded into collapse. Victory ships could sustain damage that would have sunk a Liberty ship and still limp home under their own power. The welding sequences Hamill pioneered were formalized into detailed manuals, hundreds of pages governing every joint, every thermal cycle. Welders learned to monitor interpass temperature, halting work when the steel exceeded 400 FF until it cooled naturally. This prevented the accumulated heat distortion that had plagued Liberty construction, where welders worked endlessly on long seams until hulls warped and froze with internal stress. Quality control became almost obsessive. Each weld was subjected to magnetic particle inspection using iron powder and magnetic fields to expose invisible cracks. Ultrasonic testing verified internal weld integrity, ensuring full penetration without hidden voids. X-ray imaging captured critical joints, producing photographic proof of weld quality before launch. No ship left the yard without certification. At first, 15% of welds failed inspection, but the workforce adapted quickly. By mid-1944, the rejection rate fell below 3%, evidence of both training and precision discipline. The results were immediate and irrefutable. Between June 1944 and the war's end in August 1945, 31 Victory ships entered service, and not one suffered a catastrophic hull failure. A few developed minor cracks, swiftly detected and repaired using stress relief welding methods before propagation could occur. The contrast with Liberty ships was stark, almost cruel. The difference was measured not in theory, but in lives, missions completed, sailors saved, disasters averted. The SS Wanda Fuka, a Victory ship, struck a mine off Okinawa in April 1945, tearing a 20-foot gash below the waterline. Her crew braced for the fatal fracture familiar to Liberty ships, but the crack stopped cold at the first riveted arrestor seam. She limped to port under her own power, was repaired in 6 days and returned to duty. A Liberty ship in a near-identical accident, the SS Richard Hovey, suffered a 90-foot crack along her keel and sank within 14 minutes, taking 37 men with her. Victory ships transformed the logistics of war. By mid-1944, American forces were advancing across the Central Pacific toward the Philippines and Japan. Every island required millions of tons of supplies hauled over thousands of miles of open ocean. Liberty ships could make the voyage, but only under severe limits, reduced cargo loads, slower speeds, and constant fear that rough seas might tear their brittle hulls apart. Victory ships carried full loads at their designed speed of 15 knots, 3 faster than the Liberty class, crossing typhoon-prone waters without the paralyzing dread of spontaneous fracture. The statistics told the story, from D-Day in June 1944 to VJ Day in August 1945. Victory ships moved over 18 million tons of cargo without a single loss to structural failure. They endured North Atlantic convoys where icy waters had shattered dozens of Liberty ships, and sailed the Arctic route to Murmansk, where near-freezing seas had once made Liberty service a death sentence. The SS Hobart Baker, a Victory ship, completed 17 Murmansk runs without a single crack. Her Liberty counterpart, the John Walker, developed fractures after only 2 and was retired from Arctic duty permanently. Crew morale changed almost overnight. Oral histories from merchant mariners after the war revealed the psychological toll of serving aboard ships infamous for breaking apart without warning. Men described sleepless nights, haunted by the groans of their own hulls, dreading the moment steel would split beneath them. Some refused assignments on certain Liberty vessels altogether. The Victory ships ended that fear. Sailors trusted them, pushed them, fought storms and enemy attacks with confidence in their construction. That faith translated directly into performance: faster turnarounds, greater resilience, bolder maneuvers under fire. During the Battle of Light Gulf in October 1944, 16 Victory ships braved kamikaze assaults and typhoon seas to deliver ammunition and fuel to the invasion fleet, conditions that would have doomed Liberty ships. The Victory class didn't just survive the war, they embodied its engineering triumph. Kyle Johnson's ship took near-miss bomb damage that buckled deck plates and cracked 3-frame sections, yet she continued operations, unloading cargo under fire for 4 days before withdrawing for repairs. The structural redundancy and built-in crack arrest features kept minor damage from cascading into catastrophe, a stark contrast to Liberty ships that had to be abandoned once their hull cracks spread beyond control. The economics of it were brutal, but undeniable. Each Liberty ship cost around $2 million to build, while a Victory ship cost roughly $2.6 million, 30% more expensive. But a Liberty ship carried a 4.6% chance of catastrophic failure during its service life, based on actual data through 1944, and those failures killed an average of 18 crewmen per incident while destroying cargo worth several times the ship's own construction cost. The Victory ship's zero failure rate made the extra $600,000 per vessel a bargain. Its cost recovered within 6 months through eliminated risk and reduced insurance premiums. By war's end, merchant mariners had a grim saying that captured the truth: Liberty ships were built by the mile and cut off by the yard. Victory ships were built by the inch and measured by the year. Those inches, every careful weld, every sequenced join, every obsessively inspected seam, meant decades of safe service instead of desperate prayers each time the hull groaned in cold seas. Bessie Hamill returned to civilian life in 1946 with no medals or public recognition beyond a letter from her supervisor. She never testified before Congress or saw her name cited in the technical papers that chronicled the welding revolution she'd sparked. Her insight was absorbed into the engineering establishment, rephrased in mathematical jargon, and published as laboratory theory instead of the lived observation of a night shift welder. Yet her legacy shaped modern engineering in ways that reached far beyond shipbuilding. Every welded structure built today, from skyscrapers to pipelines to pressure vessels, follows the sequencing principles first developed at Richmond Shipyard in 1944. The American Welding Society's 1947 Structural Welding Code formally codified center-outward sequencing and stress relief protocols as mandatory standards. When engineers built the Trans-Alaska Pipeline in the 1970s, they referenced Victory ship methods to prevent cold weather cracking. That 800-mile line of steel carrying hot oil through frozen ground exists because those lessons endured. Modern bridge construction inherited the same discipline. The 1967 collapse of the Point Pleasant Bridge, which killed 46 people, revealed welds made without proper sequencing that had locked fatal stresses into the structure. The post-disaster revisions to welding codes mandated the very inspection and sequencing protocols pioneered on Victory ships. The Golden Gate Bridge seismic retrofit in the 1990s, adding thousands of tons of reinforcement steel, used computer-modeled weld sequences designed to minimize residual stress, an advanced echo of the methods Hamill had tested by hand in 1943. The offshore oil industry learned the same lesson, often through tragedy. The 1980 Alexander Kielland platform disaster in Norway that killed 103 workers, and the 1988 Piper Alpha explosion that claimed 167 lives, both traced their origins to cracks in poorly sequenced welds. Each investigation rediscovered what Victory shipbuilders had already proven 40 years earlier, that residual stress kills. Modern offshore standards now require post-weld heat treatment for all critical joints, the direct descendant of the ovens Kaiser installed at Richmond's prefabrication shops. Even nuclear engineering bears her signature. The massive steel vessels that contain reactor cores must be absolutely free of internal stress points. Their welding sequences are planned with computational precision, simulating thermal effects and residual stresses before the first arc is struck. Once complete, entire reactor shells are baked in enormous furnaces to eliminate hidden stress. The same principle Hamill and Kaiser applied in 1944. The engineers who designed those nuclear vessels openly studied Victory ship construction as their foundation. Her insight fundamentally changed how engineers think about fabrication. Before Victory ships, design and construction existed in isolation. Engineers drew the plans, builders executed them, and few considered how process influenced performance. Victory ships proved that the sequence of building was as vital as the design itself. Modern engineering students now learn that a flawless design built with poor sequencing fails sooner than a modest design executed with precision. The 5-day construction timeline of the Liberty era was never the true miracle. Kaiser's yards could have kept that speed indefinitely, producing flawed vessels that looked seaworthy until they fractured. The real achievement was slowing down to do it right, having the courage to halt production, to listen to a welder's intuition that contradicted accepted theory, and to rebuild a process around observed truth rather than defended assumptions. That willingness to hear the worker on the floor became the seed of modern manufacturing philosophy. Every quality management system since Six Sigma, lean production, total quality management echoes that principle. The person watching the process often sees what the engineer at a desk cannot. When Bessie Hamill died in Sacramento in 1987, her obituary mentioned only that she had worked in wartime shipyards. But every welded bridge, every pipeline stretching across frozen terrain, every reactor vessel holding unimaginable pressure, and every skyscraper anchored in steel still carries her legacy. Each seam, each joint, each carefully sequenced weld is silent testimony to the woman who once asked why ships were breaking and refused to accept that's just how it's done as an answer.